Hello friends, welcome to YouTube channel Electronics. Today we will discuss about how op-amp can be used as a comparator. The topics covered in this video are: what is comparator, how op-amp can be used as a comparator, what are the design considerations in using op-amp as a comparator, inverting and non-inverting comparators, window comparator using op-amp, and finally, we will discuss some applications of op-amp comparator. A comparator is an electronic circuit which compares its two input signals. The output of a comparator indicates which of the inputs is greater or lesser. If V1 is greater than V2, output voltage becomes positive. If V2 is greater than V1, then output voltage becomes negative. Note that comparator falls under non-linear applications of integrated circuits. Suppose if you want to detect a room temperature or intensity of light according to the sensor's input, this comparator will produce an output which turns on the relay and light or buzzer will switches on. However, we can use op-amp as a comparator in open loop configuration, because op-amp amplifies the difference between its two input terminals and have a very high open loop gain of 10 to the power of 5. So very small difference between its two inputs makes the op-amp to saturate. If voltage at non-inverting terminal is higher than voltage at inverting terminal, in open loop, op-amp switches to positive saturation. If voltage at inverting terminal is greater than voltage at non-inverting terminal, in open loop condition, op-amp output will switches to negative saturation. Hence, an op-amp can compare or detect the small difference in its two inputs and switches to saturation and becomes non-linear. So, we can use op-amp as a comparator in open loop configuration. However, we must consider characteristics of op-amp before configuring as a comparator. Many op-amps have clamping diodes or back-to-back diodes between their inputs. These clamping diodes protect input stage transistors from large voltages. These diodes can cause excessive current through op-amp's inputs and damage the op-amp. So, an op-amp cannot have input clamping diodes when used as a comparator. Op-amps are designed for linear applications with negative feedback. The input voltage of an op-amp should be within the linear range. Otherwise, undesired result may occur. Before configuring the op-amp as comparator, we must consider propagation delay time. In ideal condition, there is no delay between input and output transitions. But in practical, an op-amp takes some time to recover from saturation, and almost all op-amps have internal compensation capacitor, which imposes slew rate limitations. So there is delay due to overload recovery time and slew rate, which makes an op-amp a sloppy comparator. Due to propagation delay, the output voltage transition from positive saturation to negative saturation after input transitions will look like this. The overload recovery time TOL is the time required for the output voltage to begin changing from saturated condition after a change in input voltage, and slew rate TS is how fast the output voltage can change with respect to change in its input voltage. The total propagation delay time contains effects of overload recovery time and slew rate. So, we must take op-amp datasheet before configuring it as a comparator. Op-amp open loop configuration have two voltages, positive saturation and negative saturation. If we use op-amp as comparator, we cannot easily interface with digital logic circuits. We need external circuit to reduce output voltages of op-amp. Many comparator ICs are available in market. They have low propagation delay times and higher slew rates. Output stages of these comparator ICs are open collector outputs. We need external pull-up resistor to use this comparator. Because of this open collector configuration, they produce well-limited output voltages that easily interface with digital logic. and also we can connect different comparators in a wide AND connection. So we have to select an op-amp that meets all of the design requirements. We can use TLV906XS family op-amps as comparators because these op-amps does not have input clamping diodes and has a rail-to-rail input and output with slew rate of 6.5 volt per microsecond, overload recovery time of 200 nanoseconds, and operates on low voltages from 1.8 volt to 5.5 volts. But dedicated comparator IC will be generally faster and accurate than op-amp comparator. Comparators are of two types, inverting and non-inverting. An inverting comparator in which input voltage is applied to inverting terminal and reference voltage is connected to its non-inverting terminal. If the input voltage is greater than reference voltage, then the comparator output will saturate towards negative supply. Likewise, when input is lesser than reference voltage, then comparator output will saturate towards positive supply. In non-inverting comparator, the input signal is connected to non-inverting terminal and the reference voltage connected to the inverting terminal. When the input voltage is greater than the reference voltage, the comparator output will saturate towards positive supply level. And when input voltage is lesser than the reference voltage, the comparator output will saturate towards negative supply level. Let us observe the output waveforms of an inverting comparator. To keep things simple, only positive supply is applied and negative supply connected to 0 volt or ground. Here assume reference voltage at non-inverting terminal is positive 3 volts. A triangular input voltage of plus and minus 5 volts applied to the inverting terminal. We can draw input waveform like this. Let us observe the output waveform. When the input voltage is lesser than reference voltage of plus 3 volts, output is at positive saturation. When the input voltage crosses or greater than the reference voltage of 3 volts, output becomes 0. So the output waveform of an inverting comparator appears like this. Here we can observe that output transitions from positive saturation to 0 and 0 to positive saturation occurs whenever the input signal is crossing the reference voltage. Here if you use both supply voltages plus and minus 15 volts, then output will reach negative saturation level of minus 15 volts instead of 0 volts when the input voltage is greater than the reference voltage. Let us observe the output waveforms of a non-inverting comparator. Here also positive supply voltage is applied and negative supply is connected to ground. And here also we have applied a triangular wave input of plus or minus 5 volts at non-inverting terminal and a reference voltage of plus 3 volts at inverting terminal. So the differential input waveforms appears like this. Let us observe the output waveform. When the input voltage is lesser than reference voltage of plus 3 volts, output is at 0 volts. When the input voltage is greater than the reference voltage of plus 3 volts, output reaches at positive saturation. So the output waveform of non-inverting comparator appears like this. Here also we can observe that output transitions from 0 to positive and positive to 0 occurs whenever the input voltage is crossing the reference voltage. But in some applications, it is required that comparators should detect input voltage levels that are within specific band or window of voltages. By combining the non-inverting comparator and inverting comparator, we can design a window comparator. Here, instead of one reference voltage, a window comparator will have two reference voltages. The lower reference voltage is known as lower threshold voltage and higher reference voltage is known as higher threshold voltage. To keep things simple, voltage divider network consists of three equal values of resistors. So the lower threshold voltage becomes 1/3 of VCC that is 5 volts, and the upper threshold voltage becomes 2/3 of VCC, that is 10 volts. The output voltage will be high when the input voltage is in between these two threshold voltages of 5 volts and 10 volts. Because of this type of combination, the comparator circuit will act as a wide AND connection. The final output is comparator 1 output multiplied with comparator 2 output. So, if any of the comparator output is low, in that case the overall output will become slow, and overall output will be high when both the comparators output is high. If the input voltage is lesser than the lower reference voltage of 5 volts, then the first comparator, that is inverting comparator, output will be high, and the second comparator output, that is non-inverting comparator output, will be low. So overall output becomes low. If the input voltage is in between lower and upper threshold voltages, then both comparators outputs will be high. So the overall output becomes high. If the input voltage is greater than the upper reference voltage, then comparator 1 output will be low and comparator 2 output will be high. So the overall output becomes low value. Let us observe the output waveform of a window comparator. To keep things simple, we are using only positive supply voltage to both comparators, and negative supply voltage of both the comparators will be at ground potential. Here our lower threshold voltage is 5 volts and upper threshold voltage is 10 volts, and we are applying a triangular wave input. So if the input voltage is lesser than the lower threshold voltage of 5 volts, output voltage will be at 0. When input voltage is in between lower and upper threshold voltage levels of 5 volts and 10 volts, output will reach to positive saturation level of plus 15 volts. When the input voltage crosses the upper threshold voltage of 10 volts, again our output will reaches to 0 volts. During the falling edge of triangular wave input, when the input voltage falls below the upper threshold voltage of 10 volts and higher than the lower threshold voltage of 5 volts, output will reaches to positive saturation, and rest of the cases output will be at 0 volts. The same thing will happen to the rest of the input triangular wave signals. In this way, window comparator will be able to detect input voltage levels. Now let's discuss some applications of comparator. A comparator can be used to produce square wave output from a sine wave input. Here inverting terminal is at ground potential and sine wave input signal is applied to non-inverting terminal. In this case, if we observe the output waveform, during the positive off cycle of the input sine wave, the output will be at positive saturation level, and during the negative off cycle of the input sine wave, the output of op-amp jumps to negative saturation level. The output voltage changes rapidly from plus 15 volts to minus 15 volts and vice versa. This change is so rapid, so that we get a square wave output for a sine wave input signal. By connecting a number of op-amp comparators together and applying a common input signal to them, but each comparator using different reference voltage levels, we can construct a voltage level detector circuit. To keep the thing simple, we are using 5 equal value of resistors in voltage divider network. The bottom comparator will get reference voltage of 1/5 of the total supply voltage, that is 1 volt, and rest of the comparators will get 2 volts, 3 volts and 4 volts reference voltages respectively, and all 4 comparators are non-inverting comparators. Output of each comparator turns on or off the LEDs connected to them according to the input voltage level. Let's observe this. If the input voltage is greater than 1 volt, then the lower comparator A4 output will be high, so it turns off the lower LED 4. When the input voltage is greater than 2 volts, then both A3 and A4 comparators outputs are high, so LED 3 is also off along with LED 4. When the input voltage is greater than 3 volts, then comparator A2 output will also becomes high. So LED 2 is also off along with LED 3 and 4. And when input voltage is greater than 4 volts, then comparator A1 output becomes high. So all LEDs will be switched off. During the falling edge of the input signal, LED 1 to LED 4 will switch off sequentially according to the input voltage level. So by setting the values of resistors in the voltage divider network, the comparator can be configured to detect any voltage level. We can use this type of circuit to detect battery condition monitor by just reversing the LEDs and connecting them to 0 volts instead of VCC. One more thing to consider is we have discussed that ideal condition of input signal without any noise. So the output will appear like this. But in practical conditions, if input signal have noise, because of this output may get affected like this. And due to open loop configuration, comparators are not immune to external noise. So to resolve this problem, comparators are used with some hysteresis, or we can say that positive feedback is provided to comparator circuit. These kind of circuits are known as Schmitt trigger circuits. By providing positive feedback, we can increase the noise immunity of this comparator. We will discuss this in another video. That's all about op-amp as comparator. I hope in this video you have understand how to design a comparator circuit using op-amp. So if you have learned from this video, please do mention them in the comment section below. Thanks for watching this video. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe my YouTube channel and turn on notifications for more such videos. My next video is op-amp as Schmitt trigger. Have a nice day.